I'm your host Chaos Dubs, and today we're jumping back into some 3D printing and design content. In part 2 of this Industry Innovating 3D printing series, we're going to dig into our material choice, how we chose it, and the steps we took to figure out what works best, as well as how we navigated some of the challenges associated with using the filament we chose. Before we begin, this is your chance to become a pirate. We just launched a new line of merch that you are going to love. Check out our merch booth to say fuck everything and become a pirate. Plus, check out our other offerings from our all over print bucket hats, neck gaiters, flags, clothing, and more. Support the channel, show some love, and flaunt your inner pirate for the world to see. Have a peek at chaosdubs.myshopify.com. Without further ado, let's dive in. In the previous episode, we discussed the thought process involved with beginning the manufacturing, design, and production of this innovation, as well as choosing a printer that has the capabilities necessary for the task. This episode is focusing on the next logical step of the process, which is choosing the right material for the application. For this particular application, Mike's job requires a very specific standard, and we will have to adhere to it closely. This product needs to be extremely strong and durable for extended use, and the material must be somewhat flexible as well as resistant to temperature changes, sunlight, rain, snow, and hail. As with everything we create, it must handle our harsh Canadian winters and drastic temperature changes as we go from -40 to +30 in the span of a few months. So this is something we're always taking into consideration. In looking into material choices available for FDM 3D printers, it can at first seem overwhelming as there's a large array of options for nearly every application. Everything from relatively cheap and not very durable plastics that are great for doing proofs of concept to wood-infused plastic, to common plastics like ABS, flexible and rubbery plastics like TPU and TPE, harder and stronger plastics like PETG that can work as finished parts, metal-infused plastics that can be sintered into metal parts after melting off the plastics, and even aerospace-grade materials that are stronger and lighter than steel and cost a fortune to acquire. 3D printing is an incredible technology that is constantly evolving, changing, and pushing the limits of what is possible in-house for a relatively reasonable investment. I am not going to go into great detail about each and every material mentioned, and certainly won't be covering every material available, as there are channels who dedicate full series to this topic and will likely do a better job than I will at covering them all. But what we will discuss is the materials we have learned about and use for our processes. The main material that most 3D printer owners use is called PLA, or polylactic acid, and it's a reasonable balance between product strength, ease of use, and cost effectiveness, but it lacks rigidity and durability in the long term. It will eventually biodegrade if left exposed to sunlight and the elements, and it does not have amazing strength or layer adhesion. Parts made from PLA may not be able to handle much abuse, or being used in and around vibrations, chemicals, or high-stress applications, and PLA doesn't stand up to severe temperature shifts very well either. Despite it being a popular choice, it simply does not suit our needs. The main material I chose to use for most of my day-to-day printing stuff is PETG. It is generally more costly than your standard PLA, but has several benefits that make it worth the increased price. Namely, it's much stronger and does not biodegrade. It has chemical and fuel resistance properties, so it won't dissolve as easily, and it has better bed and layer adhesion, making it generally easier to work with and a lot stronger in its final printed state, thus allowing use in more direct applications such as machinery parts, moving prints, brackets, and other useful applications around the house or the shop. PETG, similar to PLA, is not flexible except under very special circumstances and specific blends of plastic. So, despite its wide range of applications, it is still not what we need for this innovation. Although much less likely than PLA, parts can break and snap and don't handle extreme cold temperatures very well. So this material is also not going to work for this application. Back to the drawing board. I began to dig deeper into the materials that were available and tried to find something that had similar properties to the original injection molded parts, and even having narrowed down the playing field quite a bit, there was still many different materials and different properties held by each one. Enter flexible filament, or TPE. These thermoplastic elastomers are the surprisingly sweet solution to many of life's problems. Flexible filament includes several different blends of plastics that make up a line of products which have characteristics of both plastic and rubber at the same time, and qualities not seen in any other 3D printing filaments. Filaments like TPU, soft PLA, TPA, and PEBA, just to name a few, are all classified as TPE, and the E is for elastomers, and they are softer and more flexible than polymers. For comparison, think back now to PLA, polylactic acid, polymer being the root there, rather than the elastomer in this case. Materials that fall under this umbrella, and in many cases, namely TPU, is used in many household, industrial, and medical applications in our everyday lives, such as shoe soles, and before you ask, yes, people have successfully 3D printed shoes, which is actually pretty cool, but it's also used on caster wheels, phone cases, vehicle instrument panels, power tools, drive belts, inflatable products, and much more. Not only that, TPU is non-toxic and 100% food safe, recyclable, chemical resistant to most normal solvents, and is so flexible that it's nearly impossible to break once printed. But there's more than one type of TPU. There's softer and harder versions, as with other TPE plastics, and each one has different characteristics and needs, so this allows you to dial in your final product to suit extremely specific situations such as making gaskets, anti-slip solutions, damage protectors, and much more, really depending on your needs. Material hardness is rated on the Shore Hardness scale, and in simple terms, there are 3 levels of hardness accompanied by a number: Level OO, Level A, and Level D. Level OO Shore Hardness measures softer materials such as gel shoe inserts, gummy bears, and memory foam. Level A measures things like pencil erasers and rubber bands, and Level D measures harder materials like plastic, tires, hard hats, and shoe heels, just to name a few, with some overlap between all 3 levels. Generally, for 3D printing, 60A is going to be about as soft as you can work with, and 95A will be near the stiffer limit for flexibles, of course depending on the temperature and your printing choices, which we will discuss shortly. Other materials such as PETG are closer to 70D, being very hard and stiff. This leads us to use TPU 95A, or thermoplastic polyurethane, with a shore hardness of 95A as our choice material. This hardness is the most popular and accessible, and it works well for this application because it becomes harder in the cold weather, which increases its rigidity and strength, and yet is easy to manipulate and work with when heated or warmed up. And best of all, we haven't been able to break them, no matter how hard we try. Of course, as I'm sure you can imagine, you can adjust print settings to allow you to print with more or less infill, which essentially allows you to choose how hollow your pieces are, and this will create a pattern inside with hollow spaces similar to a honeycomb that still helps retain strength but reduces material input and cost. There are several patterns to use depending on your needs, but for an easy visual, the honeycomb analogy will do. Depending on the infill percentage you choose, you can adjust the flexibility and hardness of the material even further to dial in exactly what you need for your application, giving some of the most flexibility, no pun intended, to this material's capabilities and usefulness. When your print settings are dialed in and you're getting consistent prints, TPU layer adhesion is absolutely fantastic. Surface finish is also pretty good, particularly when you use ironing passes at the very end, and in fact, it adheres so well, many people recommend using a bed of masking tape on your print surface to prevent damage due to TPU's incredible holding power. Other filaments under this umbrella are quite the opposite and require a special glue that is quite expensive at 30 Canadian per glue stick, and it will not stick whatsoever without it, so you really can't use it. So as you can imagine, it's quite important to do your research for every filament you decide to use, as each one will require specific nozzle and bed heat settings, adhesion modifications, and changes to your print head. And that goes for basically all filaments. Of course, not everything can be amazing because this material almost sounds too good to be true, doesn't it? Well, unfortunately, printing with flexible filaments comes with several somewhat problematic caveats that you will need to deal with to get ideal results. Due to the nature of the filament being more like a wet spaghetti noodle as it comes off the roll, Bowden tube extruders, which we discussed in the last episode, are basically out of the question and become an impossibility as the material gets softer. Some users report being able to use Bowden tube printers for TPU with very specific settings and low printing speeds, but plenty more are warning of the nightmare you will face when trying to use the wrong tool for the job. And not only will you need a direct drive printer, but it will also require some specific setup, settings, and tuning to make TPEs print reliably, or at all for that matter. A longer all-metal hot end can help melt the material earlier and quicker, and in the case of the SV07 printer mentioned in the last episode, it has the longer hot end and allows printing faster even with TPU, but the SV06 will also print TPU just fine. When printing flexibles, as long as you ensure your feed wheel tension is not set too tight, and you disable filament retraction completely and remain within reasonable printing speeds, you may just be able to get some decent prints. I say may because without hands-on experience and many failures, it would be quite difficult to get the feel for the flexibles and how they react and work on different settings, speeds, tensions, and the like. When I initially began using TPU in my printer, I had plenty of struggles and in my learning processes jammed up my extruder several times, nearly to the point of being unable to rescue it. TPU would jam up and wrap around all of the drive gears several wraps, causing the prints to fail and a real mess to fix. After implementing the aforementioned steps of disabling retraction and setting the drive wheel tension just right, and that's actually much looser than one may expect, I started to get reliable and consistent prints using TPU. For a while, we were printing consistently day and night on several printers and having pretty good success and consistent repeatable results. That is until one morning I awoke to find my SV06 acting a fool. As I went to investigate the expected to be soon completed print job, and I found the printer head well above the deposited filament doing all of nothing, I assumed it was simply another jam for one reason or another. But this would be quite strange because the jamming issues were solved as far as I knew. But I was wrong. It was not simply just a jam. Something went horribly awry and I found my printer head completely encased in melted TPU. All of the hair-thin wires, the circuit board, the connectors, the nozzle, the hot end, and basically everything below the drive gears was a solid blob of TPU. It appears that the printer had a mishap where partway through the print, the filament failed to adhere to the already printed layers and instead somehow started bouncing off it and sticking. So it began sending filament upwards, and as the print head moved through its final hours of life, attempting to finish the job, it slowly committed printer side as it entombed itself in its own excrement. After spending several hours attempting to remove the TPU, which if you remember can adhere to the build plate so well that it can damage it, trying everything from scraping, chipping, and cutting, to melting with heat and dissolving with chemicals, and again remember it's mostly chemical resistant to the usual suspects, so I essentially had to give up, and the risk of cutting myself or causing further damage was just really not worth it. This required me to order a replacement extruder and wait for it to ship, but in doing so, it gave me the opportunity to upgrade the extruder to the SV07 model with a longer all-metal hot end, which will allow faster printing even on the SV06, so it's not all bad. This is when I ended up purchasing another SV06 as I was waiting for the upgraded extruder to arrive. So there was a great deal on the SV06 and it was just simply too good to pass up. And because we were now down to one printer, nearly at the finish line of printing this larger order, it made sense to get Amazon's next day delivery of the new printer and use the extruder to replace the already built and ready to run printer to finish the job while I waited for the new one to arrive. In doing so, and thinking forward, I now have 3 printers, 2 of which have the upgraded longer hot end, and now the ability to produce more products even faster for the next orders and beyond. Staying true to one of the mottos that we live our lives by, 2 is 1 and 1 is none, so grab a third and have some fun. Overall, despite the mishaps, the extra steps, modifications, and settings required to print with TPU and other flexible filaments, the experience we have had is a positive one, and in cases where you may require specific materials, flexibility, and long-lasting durable parts, such as gaskets, cases, and similar items, flexible filament is certainly worth the effort to get to know, use, and master, and is certainly worth some space in your workshop to have around. With that being said, this pretty much wraps up this episode, and as we continue the adventure through the rest of this series, we will discuss the 3D design, how I learned to do it, other problems we have solved along the way, and we're going to go over the results of all of our testing and work. For now, be sure to leave a like, subscribe to the channel, share this video to at least one person who you think may benefit from it, and head over and check out the merch booth at chaosdubs.myshopify.com. Take care, and we'll see you in the next one. Thank you for watching. Before you go, one more thing. Check out some of these related videos. You might just like them. Take care.